simple functions to deal with here. You got the square root of x and 6 minus x. R is the region bounded by the x-axis and the graphs of f and g as shown in the figure above. So the first thing asks you for the area of R. You have two options on how to find the area of R for this. So one thing that you can do is if you're just looking for the region R and you want to leave everything in terms of x as it is, you can just do, you could do the integral from 0 to 4 of the square root of x dx plus the integral from 4 to 6 of 6 minus x dx. So what you're doing there is you're just splitting this in half, and or not in half, but you're splitting it right here at that intersection. And this will give you the area under the curve for f of x, and the second one will give you the area under the curve for g of x. So this is a pretty straightforward way to do it. It's not going to be terribly difficult. But the other option is, if you want to write this as one integral, you can do it in terms of y. So if you solve both of these equations for y, so this one right here would be yx equals y squared. And then this one right here, that would be y equals 6 minus x. So that's y minus 6 equals negative x. So that would be 6 minus y equals x. So this one right here is x equals 6 minus y. The work is a little easier if you do it in terms of y. Because if you do this in terms of y, you're going to integrate the right function, which would be 6 minus y, minus the left function, which would be y squared. You would do this with a dy here because it's in terms of y. What would your limits be if you do it in terms of y? 0 to 2. So you don't have the square root to deal with if you do it this way, and it kind of puts it all together. Plus you're integrating from 0 to 2, which is going to be easier to plug in. So it's a little bit quicker to do it this way, but either way is perfectly acceptable. I'm going to work this one out this way. So if we were to integrate that, we're going to get 6y minus 1/2 y squared minus 1/3 y to the third. And we're going to evaluate that from 0 to 2, which is going to be 6 times 2 minus 1/2 times 2 squared minus 1/3 times 2 to the third. And when we plug in 0, we'll just get 0 there. So that is going to be, let's get down here, 12 minus 2 minus 8/3. Technically, you can stop here. And in fact, I don't know if there's an advantage to simplifying all the way other than I just don't like leaving it. So really probably, like real AP exam, I'd probably stop right here. But that's 30. So 22 over 3. And is that what I had on my solutions? Let me make sure. 22 over 3, yep, okay. So, and you can see, I did work it out both ways on the key if you want to see this worked out this way. You can do it this way, or you can do it in terms of y. Not a big difference in doing that either way for this. However, part B is going to ask you to do this with pieces perpendicular to the y-axis. So you're going to have to do things in terms of y for part B. So if you do that in A, you already have them solved for y for part B. Okay, questions on A? Okay, there. All right, so if we take that region And we're going to do cross sections of the solid taken perpendicular to the y-axis is a rectangle whose base lies in R and whose height is 2y. Now notice it's not 2 times its width, it's 2 times y, the y coordinate. So that's a little different than what we've seen before. So we're supposed to write, but we don't have to evaluate an integral expression that gives the volume of the solid. Make sure you pay close attention when you see this, but do not evaluate because you can waste a lot of time evaluating that if you're like actually trying to figure it out. So we don't have to evaluate, we just have to write the integral for the volume. So for this, our cross sections are perpendicular to the y-axis, which means this S right here has to be in terms of y. We got to have our S is going to be the right equation, which is 6 minus y, minus the left equation, which is y squared. That is our S for this. So our rectangle that we're going to build here has a height of 2y, and then our base would be our S right here. So our area formula is going to be 2y times S, which for this equation, that S is 6 minus y squared. So if we distribute that, we got, you don't have to distribute, but I think I will. So 12y minus 2y squared minus 2y to the third. So that is your area formula. You are going to integrate that, 12y minus 2y squared minus 2y to the third. Make sure you put your dy over here on the end. Since all of your variables over here are y's, you have the dy, you need to look at the y-axis for your limits. What are they going to be? 0 to 2. Okay. You do not have to actually integrate that. So watch out for that because that's one you could do, right? It's not that difficult to do. So if you don't read carefully, you'll waste a lot of time integrating that. But it just says to write it, not evaluate. And let's make sure that looks right from what I have over here. I did not distribute the 2y on this particular problem. You don't have to, but it's the same thing. Okay, so that was our part B. Are we okay there? All right, and then C is your probably most difficult part of this. Well, kind of. There is a point P on the graph of F at which the line tangent to the graph of F is perpendicular to the graph of G. We need to find the coordinates of point P. Okay, so what we're looking at, if we extend G way on out here, we're looking for some point, maybe here, where our tangent line is going to be perpendicular to G. Right there, that's what we're looking for. This right here would be our point P. So there's several things we have to know. First of all, perpendicular, what do we know about perpendicular slopes? Opposite reciprocals. Flip and change the sign, right? So G is pretty easy to find the slope of because it's just a line. So slope of G of X, if you want, it's G prime of X, right? It doesn't, you can call it that if you want. It is going to be -1 because it's just 6 minus X, so it has a slope of -1. So your perpendicular slope, what is it going to be? 1. So we know this line right here has a slope of -1. we know this slope right here should be positive 1 for this to be the case. So when we're talking about that perpendicular slope, we're talking about, we know that f is going to have that perpendicular slope. How do we talk about the slope of f? F prime. So f is just the square root of x, which I'm going to write as x to the 1/2 power. So f prime of x would be 1/2 x to the negative 1/2. So this gives us slope of f, right? Because the derivative gives us the slope of the tangent line at any point. So I'm going to write this as 1 over 2 square root of x, just to make it a little easier to deal with. Move that exponent back down to the bottom and change it to a root. So I want to know where this slope equals 1. So I just take 1 over 2 root x and set it equal to 1, which is, I could just cross multiply this. So 2 square root of x would equal 1. I would divide both sides by 2. So the square root of x would equal 1/2, and then I would square both sides. So x would equal 1/4. Did it ask for the x coordinate or the point? Point. Yeah. Find the coordinates of P. So you need x and y. So there's your x coordinate. So P is at 1/4. All right, how do we find the y coordinate? Plug x back into just regular f of x. So f of 1/4 is going to just be the square root of 1 over 4. Square root of 1 is 1. Square root of 4 is 2. So we get 1/2 for that y coordinate. And I believe that is all we have to do on that one, right? Yeah, I believe so. I'll flip over and check my key just to make sure I haven't messed it up. I think that's right. Okay, questions? Okay, make sure that you've got the other two ready to go for tomorrow. I'll be here for tutoring if you got any questions on those. Or if we get some time at the end, you can ask me questions if you have any. So one of these will be on the quiz. You'll also have one new one as well. So be ready for that tomorrow. I need to check your homework real quick. It was the last 3 of that worksheet, so I'm going to come around and check it real quick. You had it yesterday. Alright. Good. Those in real quick. I want to show you. Are any of you in course tomorrow? Will you be here at all? Or y'all all day down there? Okay. I'll just need you to make up your FRQ next week sometime. I'll be here Monday if you can come Monday, or if you can, or what do you have third period? Oh, is that online?
No, it's with me.
Okay. probably before school. Yes. All right. Oh, hold on. I put that in wrong yesterday. Alright. We've all got this today except for Wesley because he's not here. Hope he's alright. 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 Okay.
I saw Legally Blonde one
That movie was practically a documentary about Harvard, right? Okay. Wait, wrong thing. Hold on. Alright, let's get the answers to these real quick. Here it is. Okay. 5 is A. 6 is B. 7 is A. Um, 6 was a little bit different because, no, not 6. 7 was a little bit different because you had a quarter of a circle. So when you have a quarter circle for that, like you end up with like a base that looks something like this. When you're doing a quarter of a circle, like this is your S, and you're making, you know, these cross sections here that are, that's supposed to be a quarter of a circle there. So your area for quarter circle is 1/4 pi r squared, and for this one, that S is your radius, right? Because like the rest of the circle would go like this. So S is your radius in that case. If it's a semicircle, that's not the case, and you have to divide your S by 2. So like for this one, you just have 1/4 pi times 2x squared for that. Integrate that from 0 to 1 there. That's how you get that one. But I know that a couple of us looked at it this morning. Because it has a radius, some of you were dividing that by 2. So a quarter circle is a little bit different. Questions? Anything you guys had trouble with last night? Making sense? Okay, we're going to do some more cool stuff today. I'm assuming that I did not, this is not mine. I went and picked up football t-shirts from the library the other day. This is how they were packaged. So I'm going to assume that they sell nuts. Yeah. I did not order anything from nuts. All right. Okay, let's see. All right. I need to see if I've got my props for these things. All right. I like cross-section stuff, and I think they look cool and can make cool-looking shapes. I think these are almost even cooler. All right, so here's what we're doing today. We're going to watch this quick little video. I don't think it has sound. It doesn't need sound. So, like, here's a curve, and then we're going to take a region bounded by that curve. So we've already done that. We know how to find that area, right? And now we are going to be revolving that around an axis. So if we take that and revolve it around the x-axis, you can see it makes this cool shape over here for that. And then we are going to be able to find the volume of that figure. Or, here you can see we're doing a different shape, same curve, but a different shape, revolving that around the y-axis, which makes a really cool hat shape here. So that is what we're looking at. I think these are so cool. Alright, how do I get out of that? Okay. Alright, so, let me see if I've got my other. So here's a couple figures you can examine. Oh yeah, like and subscribe. I have subscribed. Huh? You were? Did you quit or get kicked out?
They all had a terrible drinking problem.
Right. Right. All right. Okay. So here's a couple physical examples we can see. This is a decoration for a baby shower, but it gives you a good picture. So like if we had an equation that would make this curve right here, if you take it, right now it's vertical, so we'd be spinning it around the y-axis. If you take it and spin it around the y-axis, like so, you'll get a 3D figure. This is supposed to be a baby bottle for a baby shower, but I keep it for mathematical purposes. So that is one. This one would be like a quarter of a quadratic here, pretty much. And so each, like, you can kind of think of like each little segment, this one's not smooth, right, is going to be rotated around. Take this out right here. So you're taking, like, it would be, right here would be your axis right here, and then you would have a quadratic, and you would rotate it around that y-axis. So what you would end up with, every piece would be a circle, right? Ignore the hole in the middle. That's just because it has to go on the, if it didn't have to go on that pole right there so they'd all stay together, it would just be solid, right? So you would have, all of these figures right here would be circles, right? And with any of these, like if we took this right here as well, if we were to take this and slice it, right, we'd have circles. All these would be circles because when you rotate around, you're going to create a bunch of circles is what you're doing. So I think somebody asked about that yesterday about, I know maybe Wesley was the one that was asking about like whether the figure's above or below, and we, I told you guys we wouldn't really ever have any problems where the cross-sections were circles. They would be semicircles if we were asked to do that. The main reason is because if they are circles, if our cross-sections are circles, they can be done using the method that we're going to use today, because all the cross-sections of this would be circles. Same thing with these here. Your cross-sections would be circles for that. So, oh no, I lost the pen. So, alright, so please put your computers away and quit searching for the band right now. Alright, so, did you subscribe? Okay, good. I need lots of subscribers. They're practically almost famous already. Alright, so the formula for this, if we rotate around a horizontal axis, the formula for all of these are going to be the equation of a circle. So this pi right here can go on the inside or the outside of the integral. It really doesn't matter. As far as evaluating it, it's easier to pull the pi on the outside so that you don't have to include that in your integral, but because it's just a coefficient. But you can put it on the inside or the outside. I'm using a capital R of x right here for that outside radius. So it's pi r squared, and you're evaluating it from A to B. In a lot of ways, it's the same as the cross-section stuff. It's just our cross-section is always going to be a circle, pi r squared. And then we evaluate it from A to B. These go on are from the x-axis. So you're taking, it's basically like the cross-sections, we're taking all those circles and adding them together by integrating. If it is in terms of y, it's basically the same equation, except for everything is in terms of y. So you have the dy on the end. This equation will be in terms of y. C and D here will come from the y-axis. Okay, so let's look at some problems for this. We are supposed to find the volume of the solid formed by revolving the region bounded by the graph of f of x equals the square root of sine x and the x-axis from 0 to pi about the x-axis. So our area that we're looking at, our region, is right here. And so what we're doing when we rotate here is we're taking, in this case, we're rotating around the x-axis. So it's like we're taking a slice right here. Okay? And we are going to rotate that around the x-axis. Maybe that whole back side needs to be dotted. But it's going to create a circle, right? And then we take another slice, another slice. We take all the slices and rotate it around. So this length right here is going to be our radius. I'm going to call it capital R of x. And it'll be in terms of x because we're rotating around that x-axis. In this particular case, that capital R of x is just the square root of sine x. So for these problems, our equation is always a circle because this right here was our capital R of x. The area of that is going to be pi r squared, right? Pi capital R of x squared. So we will do the integral. We'll use limits. Oh, that'll be pi, won't it? Yeah, we're going from 0 to pi. So from 0 to pi of pi r squared. So I'm going to tell you, it might, I put the pi, it's easier to evaluate with the pi on the outside. I always forget the pi on these problems, and a lot of students do, and like even I as the teacher forget the pi a lot of times. So it might be better to at least start off with the pi on the inside, so you're thinking of this as pi r squared, the equation of a circle. Because otherwise it's really easy to forget the pi. I was just working through the progress check problems the other day for this unit, and I did a problem like this, and I had everything right except for I forgot the stinking pi out front. So, if it helps, you might want to put it on the inside. So you got pi times this capital R squared, and this will be in terms of x, so put a dx here. And so, and again, that pi can go on the inside or the outside. It's part of the equation for a circle, so pi r squared. And so we'll have pi on the outside. I'm going to pull it on the outside now. We're integrating from 0 to pi, and then square root of sine of x squared is just sine of x dx. So we're going to do this one by hand because that is a very simple one to integrate. What do we get when we integrate sine x? Negative cosine x. And we are going to evaluate that from 0 to pi. So we will have the pi out front. We'll have negative cosine of pi minus negative cosine of 0. That double negative right there can become a positive. And cosine of pi, what is it? Negative 1. And cosine of 0 is 1. And so that double negative right there becomes positive. 1 plus 1 is 2. We'll get 2 pi units cubed. Here. And that'll be our answer. Okay, questions? All right. Let's do another one. Okay, we are specifying the volume of the solid formed by revolving the region bounded by the graph of x to the third plus 1, y equals 0, and x equals 2 around the x-axis. So for this, let's start by graphing that cubic. So we're going to go up 1, and then here, 2 cubed, oh wait, hold on. Let's redo that. Let's pay attention to the scale on this graph. That would be 1. This would be 3. So 1, 2, let's go off the graph over here. And we'd have here if we need it. I'm not sure if we're going to need that. So we got like this looking graph here. Then we would have y equals 0. That is going to be our x-axis. And we will have x equals 2. I really should have put more room on this graph right here, shouldn't I? Because x equals 2 would be right here. I should have put more room on this graph. We get at least a picture. Eventually that's going to cross up there, right? Since we're rotating around the x-axis, it'll be okay that we can't see that intersection right there. So this is not a vertical asymptote. This does eventually up here cross. It's just where I ran out of room because I did not put the right scale on this graph. So what we're doing here is we are revolving around the x-axis, so it's like we're taking this vertical slice right here and we're revolving that around the x-axis to make a circle. So that this right here is our radius, which is just going to be the equation of the cubic. So x to the third plus 1. So whenever we're integrating here, we're going to be integrating pi times that radius squared. This is in terms of x, so we're going to put the x on the end. What should I use for my limits? Do I look at the x-axis or the y-axis? It's going to be -1 to 2. Yeah. Okay. So to evaluate this, I would pull the pi out front. And then the x to the third plus 1 squared, we can double square that. So that's going to give us x to the third plus 2, x to the sixth plus 2x to the third plus 1 dx. We're evaluating this from -1 to 2. So we will have pi 1/7 x to the 7th plus 1/2 x to the 4th plus x, and we're evaluating that from -1 to 2. So that would be 1/7 2 to the 7th plus 1/2 2 to the 4th plus 2 minus 1/7 -1 to the 7th plus 1/2 -1 to the 4th minus 1 2 to the 7th is this going to be? This is definitely the upper limits of what you're going to have to do without a calculator. 2 to the 7th. 16, 32, 64, 128. Let me double check this. 128, 2 to the 7th. 128, yeah. So you got 128 over 7 plus 2 to the 4th is 16 divided by 2 will give you 8 plus 2. Then this is going to be a -1/7, but then when you distribute that negative, you'll get a +1/7. You'll get here a -1/2. It's going to be positive, but then you distribute this negative to it, which makes it negative, and then you'll get a +1. So that's going to be 129 over 7. We got 10, 11, minus 1/2. And, you know, for your response, you could just quit. You could have quit way back here on a free response. We're already into this. All right, if I double that, I added the 1/7 over here. So if I double that, so I can make this everything over 14, that would be 1 and 2, 58 plus 11 times 14. 140 plus 11, 151 minus 7 over 14. Oh, I'm cheating. I got 395 over 14, so 395 pi over 14. Did you guys get the same thing? I'm going to integrate this on the calculator to confirm. And if I'm wrong, I'm just going to mark it out and say they probably wouldn't give us this without a calculator. So, integrate pi times x to the third plus 1 squared, comma, x, comma, negative 1, comma, 2. $154. Chad's 3. Still didn't give me the right answer. Yeah, the calculator gives you 405. So, I don't think they're going to give you that one. I think if they give it to you without a calculator, they only ask you to set it up. If they give it to you with a calculator, of course, you can integrate it using the calculator. There's a chance. There's a chance. But also, if it's on free response, you can stop right here. You don't have to go past that point. So, that's what I would do on a problem like this, because it's unless you need to use it for something else, and usually you don't on these problems, you don't have to go past that. All right, so, last problem. Okay, this one we're going to rotate around the y-axis. So, we'll find the volume of the solid formed by revolving the region bounded by the graph of y equals 2x squared, x equals 0, and y equals 8 in the first quadrant about the y-axis. So we want to graph this. Y equals 2x squared. 0 squared is 0. We're only looking at first quadrant, so we're not going to graph over here. If we plug in 1, we would get 2. If we plug in 2, we're going to get 8. So we got this sort of like tall, skinny parabola here. It would do the same on the other side, but we're not really interested in that because it only asks us for first quadrant. X equals 0 is the y-axis, and y equals 8 is the horizontal line at 8. And so we're going to end up with this region right here. So we are taking this region and we are going to have a horizontal slice this time. So if we're rotating around that y-axis, we've got this horizontal slice that gets rotated around this way. So this is our radius, but it's going to be in terms of y. So this equation right here, y equals 2x squared, has to be solved for the x. So we divide by 2. So we got y over 2 equals x squared. We will square root both sides. So that is going to give us x equals the square root of y over 2. You could do plus or minus, but you're looking at the right-hand side of this, so you want to do the positive there. So our formula here would just be right minus left, but this is just 0, which is what you're going to see today. So you got square root of y over 2. So that is our radius. So our area is always of a circle for these problems. These rotation problems, it's always a circle. So we're doing pi times that radius squared. We put a dy on the end. What should our limits be? 0 to 8. Because since we're in terms of y, we're looking at that y-axis. So it's going to be 0 to 8, not 0 to 2 for this one. So square roots are actually kind of a good thing on these because they usually cancel out with the square there. So that pi, I'm going to pull out front. I'm going to write this just as 1/2 y because when we take the square root of the square, it is going, or the square root is going to cancel out. We'll just have y over 2, which is 1/2 y. So this one I think we should be able to do without a calculator pretty easily. We're going to have, no integral symbol anymore because I'm getting ready to integrate. I'll have pi times y squared. We're dividing out front by that 2, which is going to give us 1/4 from 0 to 2. If you want, you can pull that 1/4 out because it's going to go with both. So I'm going to just put a pi over 4 here. Yes. Why did I switch? What's wrong with me? All right, so I'm going to have 8 squared minus 0 squared here. So that is just going to be pi over 4 times 64, which if I do 64 divided by 4, we get 16. Now we get 16 pi. Cubic units there. Something like this or number 1, very likely you may be asked to find the final answer without a calculator. I think number 2, they're either just going to ask for the setup or give you a calculator to do it. Okay, questions? Yes. Yes. Anytime you're rotating around the y-axis, or we'll see some different problems we're going to run into, or any vertical line, because we also, like instead of rotating it around the y-axis, we could rotate around the line like y equals 2 or something here, but that'll be a more complicated thing we'll look at later. So any vertical line that you're rotating it around, everything has to be in terms of y. You have to have a dy, y's in your equation. If you're rotating around a horizontal axis, today all you'll see is the x-axis, but that could also be other horizontal lines. It's going to have to be in terms of x. Yeah, they have to match. Yeah. And so, this equation looks like it's going to be x's when you're looking at the equation, but since you're rotating around the y-axis, you have to change stuff to y for that. So, your assignment is from the textbook today. 1 through 7, 9, 13A, 14B, 25, and 33. And we've got a pretty good amount of time to work on it. Remember, you also have corrections due on Tuesday and FRQ tomorrow, so you're welcome to work on those things as well right now if you would like to. Whatever is the best use of your time.
Oh, maybe that's not what's in the short. You told me it was due today and not tomorrow. No, I said it was due today. I know, I don't know why you did that. You're supposed to tell me it was due Friday.
The corrections, or
Correct.
yeah,
Yeah,
they're.
you texted me at 9:30 last night and said, "Are the test corrections due tomorrow?" You tell them no. I said no, they're due Friday. We're trying to help him out because he needs to stop procrastinating.
Well, I mean, it's not a bad idea to tell
And
them.
then he said, "I'm going to kill that skinny word they can use." That actually hurt.